All right, welcome back. Now we're going to talk about part two. The second concept we're going to talk about today is variance. Now, variance is an equally important concept as expectation. Variance measures the spread of the data. So, expectation tells you where the average point is. Variance tells you how spread out the data is. So over here you see two distributions. Obviously, the orange distribution, the data is more spread out. Notice how in the blue distribution, most of the data ranges between -2 to 2, right? However, for the orange distribution, the data ranges all the way to roughly -6 to +6. So you can tell that the orange data is much more spread out. Over here, if you look at two distributions, right, this one, you can tell, has a much smaller spread, and therefore this one is actually the blue one. Whereas this one over here is comes from the orange one, and you can see that this is much more spread. So in this cases, the variance of the second table, this one, will be much larger. To find the variance, we simply need to calculate on average how far each sample is from the center. So you just need to see how far it is from the center. Let's take a quick look on how to do this. Let's take this data set over here, 0, 1, 2, 3, 4, and we know the average of this is 2. So to find the distance from the center, we take each point and subtract away from the center. That will give us the distance away from the center for each sample. So over here, 0, 1, 2, 3, 4, I take 0, 1, 2, 3, 4, each one of them subtracting from the center, telling us that the difference in distance is -2, -1, 0, 1, and 2. Okay. Now, if we were to find the average, we took all the distance from the center and averaged them together, which we summed them up and divided by n. Notice that when we try to average them together, the result is 0. This obviously doesn't make sense because this data has some kind of spread. Therefore, how can the spread be 0? And that the reason for that is because when you just take the difference directly, sometimes you can have negative and sometimes you can have positive, and they cancel each other out. And when they do cancel each other out, it doesn't really make sense. So what you want to do is you want to always make sure the distance concept is a positive value. So for variance, what mathematicians decided to do is to just always square the distance. So over here, you find the distance from the center and then you square it and then you average that. That is the equation for variance. Okay, so it's not the average distance from the center, it's the average distance square from the center. Now, this equation is the variance if you're calculating and you have the total population. However, empirical variance is when you don't have the population. And notice that it turns out that you need to divide by n minus 1. And this will give you a slightly more accurate result when you don't have the total population. Okay. Now, there are various forms of variance. We talked about the variance, the way we would write it is var of x. And with variance, you want to essentially, is like I said, is the average distance from the center square, right? But just like mean, notice that whenever we're taking the average of something, we can convert it from a probabilistic perspective. So now we take the event multiplied by the probability instead of divide by n, right? The difference is the same. Over here, we're looping through every single sample. Over here, we're looping through the possible events, okay? Because each possible event has a probability, okay? All right, so if we're working with the total population, then for this continuous domain, this equation transforms into an integral. Okay? If it's discrete, it's the same equation. Okay. Now, another thing you want to notice that when we have expectation, we previously learned that we can also have expectation function, right? So if it's a function, we will essentially plug the function in here and multiply it by the probability. So what I'm saying here is variance of x is just the expectation, so the average distance from the center square. Okay. All right, now I want you to pause the video and kind of take a second to see if you absorb, try to logically think through from the what we talked about and come up with the two separate equations. There are two ways to calculate variance. See if you can remember the storyline and come up with the equation yourself. Okay, pause the video. We're going to go on. Okay, so from variance, that leads us to this concept called standard deviation. Remember, I told you the variance is the average of the distance from the center square, right? So the key here is square. So that's the average distance square, but we normally want to know the average distance itself. So what we do is to take the square root of the variance, and that will give us the sense of what the average distance is from the center. And when we take the square root of variance, it leads us to the equation of the standard deviation. So whenever we're talking about a standard deviation, what we're really saying is what is the average distance from the center, right? So if after one standard deviation, it goes this way, right? Plus or minus one standard deviation. That means on average, 69%, roughly 69% of the population are within this distance. Okay? So 68% of the population falls within the first one, and 95% falls within the second. Okay? All right, now you want to pause the video and see if you can calculate the empirical variance. Okay, pause. The solution is on the next page. And when you go out and work, you want to calculate variance, you don't need to use that equation. In NumPy, you simply can type var, variance. And if you want to take the standard deviation, it's the STD, standard deviation, not the disease. And notice how if you take the square root of the variance, you get the standard deviation as well. Okay? Right, now that we've gone through the concept of variance, let's talk a little bit about this thing called the bias variance trade-off. So what is a bias and what is a variance? So variance is bias is saying on average whether on average you are hitting the target. So over here is an example of low bias, low variance. So notice how on average these points are hitting the target. Therefore, it's low bias. And over here, even though it's kind of off, but on average, it is also hitting the target. So the average is hitting the target. However, this has a high variance because the data has large variation. There are other cases where you have high bias. Notice how the average is far away from the center. But at least it's low variance because the data is tightly packed together. And in this particular example, you have high bias and high variance. So in these cases, the ideal case is basically you want low bias and low variance. Okay. Now, and if we actually try to show models of low bias and low variance, over here is an example of low variance. So there's not much variation to your model, but the bias is a bit higher. Over here, notice how you have very high variation to your model, but it's doing a better job fitting the points. Therefore, it's lower in bias. So historically speaking, there's been we believe in this thing called a bias variance trade-off. Bias variance trade-off, where you want to minimize both bias and the variance. However, it gets to a point that you can no longer lower the bias without hurting the variance, or improving the variance without hurting the bias. There's a point where you kind of like it becomes a trade-off. Okay, so for a long time we thought this is a rule that there's a trade-off, and later on we discovered that this rule could be broken with very large neural networks that are trained for a very long time, which is very interesting. Um, so bias variance trade-off is still interesting concept today, but we don't really talk about it as much anymore. Well, the bias variance trade-off idea leads us to this concept called model selection. Model selection. Remember, currently we learned the linear model and the polynomial model. We learned both, right? And polynomial, you can have second, third, fourth, whatever order you want. Now, the question is, how do you know which model to pick? The process of picking a model is called model selection. You're trying to select the appropriate model. And over here, you can see three possible cases. In the first case, this one curved, but you use the line. So in this particular case, the line is insufficient to model the data. And in those cases, we have a model that's too simple for more complicated data, and this is called underfitting. Underfitting. In the second case, we got just right. We got just right the right kind, and this is when you pick the right model. And in the third case, this is way too complicated. Notice how the variance is very large, and the bias is not that good either. In this case, that means you use a model that's way too complicated. And therefore, we have a situation that is called overfitting. So, in all these cases, you want to find the model that just has the right complexity so you can avoid underfitting and overfitting. Okay, so how can we do that? How do we pick the model that essentially allows us to do this? Historically, there's been two ways to do it. There's the AIC BIC method, which nowadays is not used as much anymore. Today, we tend to use the split data into train, validate, and test. So we're not going to go over this. Let's go over the one that we do today more commonly. So the way we achieve this is, let's say we have 100% of the data. What we do first is we split the data into three parts. It's called training, validation, and test. Okay. Now, with training, it's the largest portion. It tends to be 10%, but it could be 70. Validation is smaller, and test is also small. Okay, so 10%, 10%, 80%. So what we do is, once we split the data into these three sets randomly, you're randomly splitting them, we first, let's say we have three models that we're testing: linear, poly second order, poly third order. Okay, so we're deciding which model to pick, which one should we use. So we basically take the training data and just train all three of them. We do all three. Once we've done all three of them, okay, now we have trained the function. We call this function 1, function 2, and function 3. So we train three models, resulting in three functions. Now remember, a model is basically we put the data in and you give us some kind of output. So once we have these functions, then we forget about the training. We pass the validation into each one of them. After we pass them, we can calculate the error, the mean square error. So error 1, error 2, error 3. So we find the error resulting from each model. Okay. And we use the data that's not part of the training. Okay. We use this for training and then we forget about it. Then we use this to figure out which one give us the lowest error. And in this case, let's say we decided model 2, poly 2, give us the lowest error. So now we know that we want to pick poly 2 because it performed the best in validation. And lastly, after we've decided poly 2 is the best, we use the test. Okay, so poly 2 is F2. and we put the test inside this, and then we get the error again, and we call this the final error. And this is the error you report in to your boss or in the research paper. You will report this, and this is the standard way that we basically go about like machine learning and picking model today. Okay, so so over here, I think it's a summary. Here's a train, validate, test. Step one, you train the data. Step two, you calculate the error using validation. Okay, so over here is basically what I already talked about. Now, to split the data, the way you could do it is using NumPy. Is to, let's say you have this data right here. Let's say this is your data, and what you do is you put the data and your label into train test split. It's a library you import, train test split, and then it will simply split them. So this is train, and then there's the rest. So this give you the x. So this, what I pick, test size. So I say test size is 20%, and the result is you're going to get 80% here, and you get 20% here. So now this is your train. Once you have this 20%, you run this again using the 20%, and then make sure you're splitting it 50-50. When you split it 50-50, then now you have 10%, 10%. And this will be your validation, and this one will be your test. Okay? So this is how you go about doing it in code. Now, let me give you guys some ideas. Even though the models you guys are learning are really, really simple, they're the simpler models. It turns out that all these simple models works really well in biology, in physics, right, and medicine. So these simple models has been working for a very, very long time. And here at the university, I periodically like to highlight some of the work that I've done with professors around. So we have a professor here at Northeastern, and she studies basically she studies like basically babies like neurological development. So she's part of the psychology, and she studies them based on how they suck pacifiers. And the idea is babies can't tell us, they can't really talk. So we don't know how well they are doing neurologically speaking, and how well um, they are developing, right? So since baby can't talk, the only thing we can really do is maybe study whether the way they suck their pacifiers like is correlated is with the neurological development. And therefore in this case you can kind of collect the data of the baby's age. So here you collect the data baby's age, and over here you can collect the data on how well the baby sucked the pacifier, maybe how long they suck the pacifier, how repetitive they suck the pacifier. So by collecting these data, you can essentially run a regression where, given the pattern, that we can predict the average age of the baby, right? So if we have a pattern and we have a certain age that we predict, therefore, if the pattern predicts a lower age than what the kid actually is, it's kind of saying that the kid's neurologically development is kind of delayed. Or if they are higher, then it's saying that their neurological development is um, like advanced, right? So this is a way of measuring kids' neurological development, and this kind of research is exactly why knowing data science is really, really useful. Okay, so this is just a quick example how things you guys learn can actually be used. So here we're done. I want you to practice what we learned. Once again, pull out the stock price, and this time I want you to split the data between train and validate. Make sure you pre-process the data, and now you want to see if a linear versus polynomial does better. Try these models, and And that's it. I think that's it for today, for today's class. Okay, have a good day.